Hello there, and welcome to this gentle exploration of the quantum realm, where particles dance through barriers and reality itself becomes wonderfully uncertain. Tonight's peaceful journey ventures into one of the most remarkable phenomena in physics: quantum tunneling, a process so extraordinary it sounds like science fiction, yet it's happening all around us every moment of every day, powering the very stars above and the technology in your pocket. Before we slip through the invisible walls of the quantum world, I'd love to know where you're listening from tonight and what drew you to this curious corner of physics. Perhaps you've heard whispers of particles behaving impossibly, or maybe you're simply seeking a calm way to unwind with the wonders of science. If this gentle voyage brings you peace or sparks your curiosity, I'd be ever so grateful if you gave the video a like and perhaps subscribed. It helps this little sanctuary of science reach others who might find solace in the strange beauty of our universe. Now, I do hope this exploration is soothing rather than startling, but if quantum mechanics does keep you awake, well, at least you'll drift off knowing something magnificent about the hidden workings of reality. So settle in, let your thoughts soften, and prepare to discover how the impossible becomes inevitable in the quantum realm. Quantum tunneling is perhaps one of the most poetic violations of our everyday experience. Imagine, if you will, throwing a tennis ball at a brick wall. In our familiar world, that ball bounces back every single time. The wall is simply too high, too solid, too real. But in the quantum world, something extraordinary happens. The ball doesn't just bounce back. Occasionally, it passes straight through the wall as if the bricks were made of morning mist, emerging unharmed on the other side. This isn't mere metaphor, it's the daily reality of particles smaller than atoms. Electrons, photons, even entire molecules routinely accomplish what our classical intuition insists is impossible. They encounter energy barriers that should stop them cold, yet some fraction of them glide through as if those barriers were mere suggestions rather than absolute prohibitions. The phenomenon rests on one of quantum mechanics' most fundamental principles: the wave nature of matter. Every particle, no matter how tiny, exists not as a solid little sphere, but as a probability wave, a ghostly cloud of potential that describes where the particle might be found when observed. These waves don't have sharp edges. They fade gradually, like ripples on a pond, growing fainter, but never quite reaching zero. When a particle encounters a barrier, something beautiful happens. Instead of stopping abruptly the way a classical object would, the particle's wave function seeps into the barrier itself. It diminishes, yes, becoming exponentially weaker with each step, deeper into forbidden territory, but it doesn't vanish entirely. If the barrier is thin enough, a portion of that wave emerges on the other side, and where there's a wave, there's a probability of finding the particle. Picture it like this. Imagine you're walking through a thick fog that grows denser and denser with each step forward. Most of the time, you turn back, defeated. But occasionally, just occasionally, you push through to find clear air on the other side. The fog represents the energy barrier, and your successful passage represents quantum tunneling. The particle doesn't break through the barrier or climb over it. It simply appears on the other side with a probability that depends on the barrier's height and thickness. This probability can be vanishingly small for large barriers, but it's never quite zero. In the quantum world, even the smallest probabilities become certainties given enough attempts. It's rather like buying lottery tickets. If you buy enough tickets, eventually you'll win. Except in quantum mechanics, particles are buying trillions upon trillions of tickets every second. The mathematics behind tunneling is elegant in its simplicity. The wave function that describes a particle's quantum state follows what's called the Schrödinger equation, and when this equation encounters a potential barrier, it doesn't simply stop. Instead, it transforms into an exponentially decaying wave that penetrates the barrier. The probability of tunneling depends on three key factors: the particle's energy, the height of the barrier, and crucially, the barrier's width. A particle with more energy has a better chance of tunneling through, much like a stronger swimmer has a better chance of crossing a turbulent river. But even particles with very little energy can tunnel if they're persistent enough. The barrier height acts like the river's current. The higher the barrier, the more it resists the particle's passage. But again, resistance isn't the same as complete blockage. Most intriguingly, the barrier width plays a crucial role. Thin barriers are relatively easy to tunnel through, while thick ones present formidable challenges. This is why quantum tunneling is primarily observed in the microscopic world, where barriers measured in nanometers or less are common. In our macroscopic world, barriers are simply too thick for tunneling to occur with any meaningful probability. The effect is so sensitive to barrier width that doubling the thickness can reduce the tunneling probability by orders of magnitude. It's an exponential relationship where small changes in barrier properties lead to dramatic changes in tunneling likelihood. This sensitivity makes quantum tunneling both remarkably useful in technology and beautifully predictable, despite its seemingly random nature. What makes quantum tunneling so philosophically intriguing is that it challenges our deepest intuitions about causality and determinism in classical physics. If you don't have enough energy to overcome a barrier, you simply can't pass through. It's a hard rule written into the fabric of reality. But quantum mechanics whispers that there are no hard rules, only probabilities and possibilities. The particle doesn't gradually gather energy to overcome the barrier, nor does it find a secret passage. It simply exists on both sides of the barrier simultaneously in a very real sense, until the moment of observation collapses this superposition into a definite location. This isn't merely a limitation of our knowledge, it's a fundamental feature of reality itself. Consider the temporal aspect of tunneling. The process appears to be instantaneous. There's no journey through the barrier, no gradual seepage from one side to the other. The particle is either reflected back or transmitted through, and this transmission seems to happen faster than light could travel the same distance. This has led to fascinating debates about causality and the nature of time itself in quantum mechanics. Some interpretations suggest that tunneling particles experience a kind of temporal paradox, where the time spent inside the barrier is effectively zero or even negative. This doesn't violate special relativity because no information travels faster than light, but it does hint at the strange relationship between quantum mechanics and space-time. The uncertainty principle also plays a crucial role in tunneling. Formulated by Werner Heisenberg, this principle states that we cannot simultaneously know both the position and momentum of a particle with perfect precision. The more precisely we know one, the less precisely we can know the other. This isn't a limitation of our measuring instruments. It's a fundamental property of reality. Near a barrier, the uncertainty principle creates a window of possibility. If a particle is localized near the barrier edge, there's necessarily some uncertainty in its momentum, and hence its energy. This uncertainty can be just enough to allow the particle to borrow energy from the quantum vacuum itself, temporarily boosting its chances of tunneling through. This energy borrowing isn't free. It must be repaid quickly according to the time-energy uncertainty relation. But if the barrier is thin enough, the particle can tunnel through and repay the energy debt on the other side. It's like a cosmic loan system, where the universe itself acts as a benevolent banker, accepting very short-term debts in exchange for remarkable phenomena. The implications of quantum tunneling extend far beyond academic curiosity. This phenomenon is the beating heart of countless technologies that surround us every day, from the smartphone in your pocket to the nuclear fusion reactions that power our sun. Quantum tunneling makes the impossible possible and the theoretical practical. In the gentle interplay between waves and barriers, between probability and certainty, between the possible and the actual, quantum tunneling reveals something profound about the nature of reality itself. It suggests that the universe is far more interconnected and possibility-rich than our everyday experience might suggest. Walls are not absolute boundaries, but temporary obstacles, and even the most insurmountable barriers can become doorways given enough patience and quantum persistence. As we prepare to explore specific examples of this phenomenon in action, remember that quantum tunneling isn't just a curiosity relegated to laboratory experiments. It's a fundamental process that shapes everything from the chemistry of life to the death of stars. It's happening around you right now, in the circuits of your devices, in the cells of your body, and in the vast cosmic dance of matter and energy that surrounds us all. The quantum world, with its tunneling particles and probability waves, might seem alien to our everyday experience, but it's perhaps the most intimate aspect of reality. The very atoms that make up your body owe their stability to quantum effects. The thoughts flowing through your mind depend on quantum processes in your neurons, and the light reaching your eyes from distant stars carries the quantum signature of tunneling events that occurred millions of years ago. In this strange and beautiful realm where particles walk through walls and possibilities become realities, we find not chaos but a deeper order. Not randomness, but a more subtle kind of logic. Now imagine standing at the edge of a vast underground cavern, watching as a gentle stream of water somehow flows upward through solid rock, defying everything you thought you knew about physics. This impossible sight captures something profound about quantum tunneling, where the very foundations of reality operate on principles that seem to mock our everyday experience. We've established that particles can pass through barriers that should be impenetrable, guided by the mysterious mathematics of wave functions and probability. But here's where things become truly extraordinary. The implications of quantum tunneling extend far beyond abstract physics into the very fabric of existence itself, touching everything from the warmth of sunlight to the thoughts forming in your mind right now. Consider the sun for a moment. That brilliant orb that rises each morning casting shadows that dance across your garden exists because of quantum tunneling. Deep within the sun's core, temperatures reach about 15 million degrees Celsius. While that sounds impossibly hot, it's actually not quite hot enough for nuclear fusion to occur, according to classical physics. The protons in hydrogen nuclei carry positive electrical charges, and like charges repel each other with tremendous force. For fusion to happen, these protons need to overcome what physicists call the Coulomb barrier, an energy wall that should require temperatures of around 100 million degrees Celsius. Yet, fusion happens anyway, billions of times per second, because protons tunnel through this energy barrier. They approach each other, their wave functions overlap, and suddenly they find themselves on the other side of the electrical repulsion, close enough to fuse into helium and release the energy that eventually becomes the light streaming through your window. Without quantum tunneling, stars would be cold, dark spheres of gas, and life as we know it simply couldn't exist. This stellar alchemy reveals something profound about the nature of reality. The universe operates on two levels simultaneously. There's the classical world of our direct experience, where objects have definite positions and follow predictable paths. And there's the quantum realm beneath it all, where particles exist in superposition and tunnel through barriers that should be absolute. These two realities don't conflict. They complement each other like layers of a complex symphony. But quantum tunneling doesn't just power stars, it's humming quietly in the technology around you right now. If you're listening to this on a smartphone, tablet, or computer, you're holding a device that wouldn't exist without tunneling effects. The flash memory storing your photos, the processor executing instructions, even the screen displaying these words all rely on the controlled manipulation of electrons tunneling through barriers. Take flash memory, for instance. When you save a photo or document, electrons are literally tunneled through an insulating barrier onto what's called a floating gate. They become trapped there, representing a stored bit of information. To erase the data, an electric field is applied that allows the electrons to tunnel back out. Your device is constantly orchestrating billions of these microscopic tunneling events, each one a small miracle of quantum mechanics made practical. The scanning tunneling microscope represents perhaps the most elegant application of this phenomenon. This remarkable instrument can image individual atoms by measuring the tiny current that flows when electrons tunnel between a sharp metal tip and a sample surface. The tunneling current is exquisitely sensitive to distance. Move the tip just a fraction of a nanometer closer to the surface, and the current increases exponentially. By scanning this tip across a surface while keeping the tunneling current constant, scientists can map the atomic landscape with breathtaking precision. Through these microscopes, we've gained our first direct glimpses of the atomic world. We've seen the hexagonal patterns of carbon atoms in graphite, the regular arrays of silicon atoms on computer chips, even individual molecules arranged like tiny sculptures on metal surfaces. It's as if quantum tunneling has given us a new sense, a way to feel the atomic texture of matter itself. But perhaps the most profound tunneling process happens in the most mundane of places, your own body. Every time you think a thought, feel an emotion, or form a memory, enzymes in your cells are facilitating chemical reactions that rely on quantum tunneling. These biological catalysts work by creating pathways that allow particles to tunnel through energy barriers that would otherwise make life's chemistry impossibly slow. Consider the enzyme catalase, which protects your cells from damage by breaking down hydrogen peroxide. Without this enzyme, the reaction would occur so slowly that toxic peroxide would accumulate and destroy your cells. But catalase creates a tunnel through the energy landscape, allowing the reaction to proceed at the speed of life. Some researchers suggest that even the transfer of electrons in photosynthesis, the process that converts sunlight into the chemical energy that powers nearly all life on Earth, involves quantum tunneling effects. This raises a fascinating question. Are we, in some sense, quantum beings? While our bodies operate primarily in the classical realm, they're built upon and sustained by quantum processes. Every breath you take, every heartbeat, every moment of consciousness emerges from the complex interplay of classical and quantum physics. You exist at the intersection of these two realms, a classical being sustained by quantum foundations. The tunneling effect also illuminates something beautiful about the nature of barriers themselves. In our everyday experience, a wall is a wall. If you can't climb over it, go around it, or break through it, you're stopped. But quantum mechanics suggests a more subtle perspective. Every barrier is also a potential pathway. Every obstacle contains within it the seeds of its own transcendence. The question isn't whether passage is possible, but how probable it is. This probabilistic nature of tunneling reveals the universe as a place of infinite possibility, where even the most insurmountable challenges contain hidden doors. A particle approaching a barrier doesn't know whether it will tunnel through or be reflected back. It exists in a superposition of both outcomes until the moment of interaction. In that sense, the universe is constantly surprising itself, constantly discovering new paths through the landscape of possibility. The mathematics of tunneling probability depends on several factors: the height of the barrier, its width, and the energy of the approaching particle. Higher barriers are harder to tunnel through, as are wider ones. But remarkably, no barrier is ever completely impenetrable. Even the highest, widest energy barrier has some finite probability of being tunneled through, however small. This means that in the quantum realm, the impossible merely becomes highly improbable. This principle extends to phenomena that seem to violate our deepest intuitions about causality and locality. In quantum field theory, particles can appear to borrow energy from the vacuum itself, popping into existence for brief moments before disappearing again. These virtual particles, as they're called, can tunnel through barriers using energy they don't technically possess, paying back the loan so quickly that the uncertainty principle allows the transaction to slip by unnoticed. It's as if the universe operates on a kind of cosmic credit system, where particles can temporarily exceed their energy budgets as long as they settle their accounts within the time limits set by quantum uncertainty. This leads to the remarkable phenomenon of vacuum fluctuations, where the empty space around you is actually seething with virtual particles, constantly appearing and disappearing, creating a quantum foam at the smallest scales of reality. Some theories suggest that the entire universe itself may have originated from a quantum tunneling event. In this scenario, our cosmos began as a quantum fluctuation in a pre-existing space, tunneling from a state of nothingness into existence. The Big Bang, rather than being a classical explosion, might have been the ultimate tunneling event, where the universe itself passed through the barrier between non-existence and existence. This perspective casts our entire reality in a new light. We might be living inside the aftermath of the greatest quantum tunneling event in history, a cosmic probability wave that collapsed into the rich, complex universe we inhabit. Every star, every planet, every living being would then be a consequence of that primordial tunneling, ripples in the quantum field that first learned to tunnel through the ultimate barrier. The contemplation of quantum tunneling also offers a unique perspective on the relationship between the possible and the actual. In classical physics, events either happen or they don't. But in quantum mechanics, every event exists in a superposition of happening and not happening, until observation collapses the wave function into a definite outcome. Tunneling embodies this quantum ambiguity perfectly. The particle both tunnels through and doesn't tunnel through the barrier simultaneously, existing in a ghostly superposition until the moment of detection. This quantum indeterminacy doesn't represent a limitation of our knowledge, but rather a fundamental feature of reality itself. The universe, at its deepest level, appears to be probabilistic rather than deterministic. Events unfold not according to rigid laws, but according to probability distributions that shape the likelihood of various outcomes. Quantum tunneling is perhaps the most accessible window into this probabilistic nature of existence. As we drift toward the edges of sleep, these quantum mysteries take on an almost dreamlike quality. The idea that particles can exist in multiple states simultaneously, that barriers can be both impenetrable and permeable, that the universe itself might operate on borrowed time and energy, all of this resonates with the fluid logic of dreams. Perhaps in our sleeping minds we intuitively understand something about quantum reality that our waking consciousness struggles to grasp. The gentle rhythm of quantum tunneling continues around us always, a subtle dance of possibility and probability that sustains the very foundations of existence. Standing at the edge of the known universe, peering into the vast expanse of possibility, we find ourselves confronting one of the most profound questions in all of physics. What lies beyond the barrier of impossibility itself? We've journeyed through the mathematical poetry of quantum mechanics, witnessed particles dancing through walls as if they were mere suggestions, and marvelled at the delicate choreography of probability waves. But now, dear wanderer, we must venture deeper into the implications of this quantum mystery, for tunneling is not merely a curiosity of the subatomic world, it is the very heartbeat of existence itself. Consider for a moment the sheer audacity of what we've discovered. In our classical understanding, a barrier is absolute. A wall stops you. A mountain blocks your path. Energy requirements are non-negotiable. Yet quantum tunneling whispers a different truth, that the universe operates on a currency of possibility rather than certainty, where even the most fundamental laws bend to accommodate the impossible. This is not magic, though it feels like it. This is the universe revealing its most intimate secret. That reality itself is far more flexible, far more generous with its possibilities than we ever dared imagine. The implications ripple outward like stones cast into still water. If particles can tunnel through barriers, what does this mean for our understanding of causality? In the classical world, cause precedes effect with clockwork precision. You push a domino, it falls. You heat water, it boils. But quantum tunneling introduces a curious wrinkle in this narrative. The particle doesn't gradually chip away at the barrier or slowly accumulate energy until it can overcome the obstacle. It simply appears on the other side as if it had borrowed the necessary energy from the future and promised to pay it back later. This isn't a violation of energy conservation, mind you, but rather a more nuanced understanding of how energy can be borrowed and returned on timescales so brief that the universe's accounting system barely notices. This temporal sleight of hand points to something profound about the nature of time itself at quantum scales. We live in a world where time feels linear, where past flows into present and present into future with the steady rhythm of a metronome. But quantum mechanics suggests that at the smallest scales, time becomes more fluid, more negotiable. Virtual particles pop into existence, borrow energy from the quantum vacuum and disappear again so quickly that they exist in the spaces between moments. It's as if the universe maintains a cosmic credit system, allowing particles to make withdrawals against future deposits, provided they balance the books before anyone notices. This leads us to one of the most beautiful and bewildering aspects of quantum tunneling, its relationship to the void itself. We tend to think of empty space as nothing, a mere absence waiting to be filled. But quantum field theory reveals that what we call empty space is actually a seething cauldron of potential, filled with virtual particles constantly appearing and disappearing, borrowing energy from the quantum vacuum and returning it in transactions so rapid they exist below the threshold of direct observation. These virtual particles aren't just mathematical conveniences, they have real, measurable effects. They contribute to the energy of atoms, influence the behavior of light, and create forces that can be detected in laboratories around the world. The Casimir effect provides perhaps the most elegant demonstration of this hidden reality. When two conducting plates are placed extremely close together in a vacuum, they experience an attractive force that pulls them together. This isn't electromagnetic attraction or gravity, it's the pressure of virtual particles. The space between the plates can only accommodate virtual particles with wavelengths smaller than the gap, while the space outside the plates can accommodate virtual particles of any wavelength. The result is an imbalance, a quantum pressure that pushes the plates together. It's as if the vacuum itself has preferences, gently nudging matter into configurations that minimize the energy borrowed from the quantum treasury. This quantum foam, as it's sometimes called, suggests that the very fabric of space-time is not smooth and continuous as it appears to us, but rather bubbling with constant activity at the smallest scales. At the Planck scale, distances so small that they make atoms look like solar systems. Space-time itself might be subject to quantum uncertainty. Distances become fuzzy, time intervals become approximate, and the neat geometries of Einstein's relativity give way to a more chaotic probabilistic foundation. It's a realm where the very concepts of here and there, now and then, become as uncertain as the position and momentum of a quantum particle. But perhaps the most staggering implication of quantum tunneling lies in its role in the origin of the universe itself. Current cosmological models suggest that the Big Bang might have been the ultimate tunneling event, where the universe tunneled from a state of non-existence into existence, from nothing into everything. This isn't to say that the universe came from literally nothing, but rather that it emerged from a quantum state where the concepts of space, time, and matter as we understand them didn't yet apply. The universe might have borrowed the enormous energy required for its creation from the quantum vacuum, with the promise of paying it back through the expansion and evolution of space-time itself. This cosmic tunneling event would have been governed by the same fundamental principles we see operating in laboratory experiments today. The wave function of the universe itself would have evolved according to the Schrödinger equation, with probabilities for different possible universes competing in a vast quantum lottery. Our universe, with its particular values of physical constants, its specific arrangement of matter and energy, its capacity for complexity and life, might be just one outcome among countless possibilities, a single thread in an infinite tapestry of quantum potential. The anthropic principle emerges naturally from this perspective. We observe a universe finely tuned for our existence not because it was designed for us, but because we exist in the branch of quantum reality where such tuning occurred. In the many-worlds interpretation of quantum mechanics, every possible universe exists simultaneously, each playing out its own cosmic symphony. We find ourselves in this particular universe not because it's special, but because it's the only one where observers like us could emerge to ask the question. This brings us to one of the most profound mysteries of quantum tunneling, the role of observation and measurement. When we measure a quantum system, we don't just passively observe it. We actively participate in determining its state. The wave function, that mathematical description of all possible states, collapses into a single reality through the act of measurement. But what constitutes a measurement? When does the quantum world of probabilities give way to the classical world of definite outcomes? The answer isn't entirely clear, and it leads to some of the most mind-bending puzzles in physics. In the famous double-slit experiment, particles behave like waves when no one is watching, creating interference patterns that suggest they travel through both slits simultaneously. But the moment we try to determine which slit the particle actually passed through, the wave function collapses, and the particle behaves like a classical object, taking a definite path through one slit or the other. It's as if the universe maintains its quantum superposition until consciousness enters the picture, at which point it chooses a single reality from the infinite menu of possibilities. This suggests a universe far more interactive, far more responsive to awareness than our classical intuitions would suggest. We are not passive observers of reality. We are active participants in its creation. Every measurement we make, every observation we conduct, every conscious choice we exercise, might be selecting one thread from the vast web of quantum possibilities, weaving our particular version of reality from the infinite potential of the quantum realm. The implications extend beyond physics into philosophy, consciousness, and the very nature of existence itself. If reality is fundamentally probabilistic, if the universe maintains multiple potential states simultaneously until consciousness collapses them into actuality, then we are not just observers of the cosmic dance, but choreographers of it. Our choices, our observations, our very awareness might be the mechanism by which the universe actualizes itself, moment by moment, choice by choice, measurement by measurement. This is the deepest mystery of quantum tunneling. It reveals a universe where consciousness and physics are not separate domains, but intimately connected aspects of a single underlying reality. The particle that tunnels through a barrier doesn't just demonstrate the probabilistic nature of quantum mechanics. It hints at a cosmos where mind and matter, observer and observed, possibility and actuality are woven together in a tapestry of such complexity and beauty that we are only beginning to glimpse its true nature. And so we find ourselves standing at the threshold of understanding, much like the quantum particle poised before its barrier. We cannot predict with certainty what lies beyond, but we know that the journey itself transforms us. Each step deeper into the quantum realm reveals new layers of mystery, new questions that challenge our most fundamental assumptions about the nature of reality. Now imagine for a moment that you're holding a compass that points not to magnetic north, but to the very heart of reality itself. As you watch its needle spinning wildly, never quite settling on any single direction, you begin to realize something profound. The compass isn't broken. It's simply trying to point towards something that doesn't exist in the way you thought it did. That something is the present moment, and the story of how we discovered its impossible nature is one of the most beautiful puzzles in all of physics. Throughout our journey into quantum tunneling, we've witnessed particles slipping through barriers like ghosts through walls, borrowing energy from the vacuum itself and existing in states of pure possibility until the moment of observation collapses them into definite reality. But there's another layer to this quantum mystery that touches something even more fundamental than space or matter. It reaches into the very nature of time itself, and what it reveals challenges everything we thought we knew about the moment we call now. In the classical world, time flows like a river carrying us steadily from past to future. Events happen in sequence, causes precede effects, and the present moment is a thin slice of reality moving through the eternal landscape of space-time. But in the quantum realm, this neat picture begins to dissolve. Particles don't just tunnel through space, they tunnel through time itself. Quantum events don't unfold in the orderly sequence we expect. Instead, they exist in what physicists call superposition, where all possible moments, all possible outcomes, all possible nows exist simultaneously until observation forces reality to choose. Consider the profound implications of this. When an electron tunnels through a barrier, it doesn't simply travel from one side to the other in some measurable duration. Instead, it exists in a state where it has already tunneled, is currently tunneling, and has not yet begun to tunnel, all at the same time. The very act of measurement, of trying to pin down when the tunneling occurs, destroys the superposition and forces the universe to retroactively decide which version of events actually happened. This leads us to one of the most mind-bending aspects of quantum mechanics: the concept of quantum non-locality in time. Just as entangled particles can influence each other instantaneously across vast distances of space, quantum events can be entangled across time itself. An observation made today can, in some sense, influence what happened yesterday. The future, it seems, has a vote in determining the past. These aren't merely abstract theoretical considerations. They have real consequences for how we understand the flow of time and the nature of causality. In certain quantum experiments, scientists have demonstrated what they call retrocausality, where future measurements appear to influence past events. It's as if the universe is constantly rewriting its own history, adjusting the past to remain consistent with the present moment of observation. But perhaps the most profound insight comes when we consider consciousness itself. If the act of observation is what collapses quantum superpositions, what forces the universe to choose one reality from many possibilities, then consciousness might play a fundamental role in creating the very flow of time we experience. Some physicists and philosophers have suggested that the present moment, that razor-thin slice of now that seems to move through time, might actually be created by the act of conscious observation itself. This idea connects quantum tunneling to the deepest questions about the nature of awareness and experience. Just as particles exist in multiple states until observed, perhaps time itself exists in multiple states until experienced. The past isn't fixed until we remember it. The future isn't determined until we anticipate it. And the present moment isn't real until we inhabit it with our consciousness. Think about your own experience of time. When you're deeply absorbed in something meaningful, time seems to disappear entirely. Hours pass like minutes, and the boundary between past, present, and future becomes fluid. In those moments, you might be experiencing something closer to the true nature of time in the quantum realm, where duration and sequence are far more flexible than our everyday experience suggests. This quantum perspective on time also offers a new way to understand memory and anticipation. Rather than thinking of memories as fixed recordings of past events, we might consider them as quantum superpositions that exist in a state of potential until the moment we recall them. Each time we remember something, we're not simply accessing a stored file, but actively reconstructing the past from quantum possibilities. Similarly, when we imagine future possibilities, we're not just fantasizing, but potentially influencing the quantum states that will determine what actually comes to pass. The mathematics of quantum mechanics suggests that the universe might be far more participatory than we ever imagined. Reality isn't simply unfolding according to predetermined laws. Instead, it's being constantly created through the interaction between quantum possibilities and conscious observation. We're not just witnesses to the universe's story. We're active participants in its ongoing creation. This participatory nature of reality extends beyond individual consciousness to the collective patterns of observation and measurement that shape our shared world. Every scientific experiment, every moment of awareness, every choice to pay attention to one thing rather than another contributes to the ongoing process of reality selection. The universe, in this view, is less like a mechanical clock and more like an improvisational jazz ensemble, where each player influences the others in real time, creating something beautiful and unprecedented with each passing moment. The implications ripple outward into every aspect of human experience. If consciousness plays a role in shaping reality through the collapse of quantum superpositions, then our thoughts, intentions, and observations might have far more influence on the world around us than we typically assume. This doesn't mean we can simply think our way to any desired outcome, but it does suggest that the relationship between mind and matter is far more intimate and dynamic than classical physics ever imagined. As we contemplate these ideas, we find ourselves at the edge of a new understanding of what it means to exist in time. We're not simply carried along by time's current, but actively swimming in its waters, each stroke of consciousness creating ripples that spread both forward and backward through the quantum foam of possibility. The present moment isn't a point we pass through, but a space we continuously create through the act of being aware. This quantum view of time and consciousness offers a profound sense of agency and responsibility. If our observations and choices help shape reality itself, then every moment becomes an opportunity to participate in the universe's ongoing creation. We're not just experiencing life, we're actively dreaming it into existence through the miracle of conscious observation. The gentle wonder of this realization is that it returns us to something our ancestors might have intuited long before the advent of quantum mechanics. The idea that consciousness and reality are intimately connected, that the observer and the observed are part of a single, unified whole, that time itself is more fluid and participatory than it appears. These insights, emerging from the most sophisticated physics of our time, echo the wisdom traditions that have long suggested that reality is far more magical, far more alive than our everyday experience might suggest. And so, as we drift towards sleep tonight, we might rest in the knowledge that we're not simply objects in a mechanical universe, but conscious participants in an ongoing act of cosmic creation. And here, at the very edge of our exploration, we find ourselves in a realm where quantum tunneling isn't just a curiosity of physics, but a mirror reflecting the deepest mysteries of existence itself. Because if particles can slip through the impossible, if reality is built from probabilities rather than certainties, then what does this mean for consciousness, for choice, for the very nature of being? Consider this. Every thought you're having right now, every decision forming in your mind, every moment of awareness might itself be a kind of tunneling event. Your consciousness, that ineffable sense of being you, navigating through the landscape of possibility, much like an electron threading through barriers that shouldn't allow passage. The neural networks in your brain, firing in patterns that somehow give rise to your inner world, operate at scales where quantum effects might play a role. Where the classical determinism of Newton gives way to the strange probabilistic dance of quantum mechanics. There's something profoundly beautiful about this possibility, that your awareness, your capacity to observe and contemplate the universe, might be intimately connected to the same mysterious process that allows stars to shine. The hydrogen atoms in your body, forged in stellar cores through quantum tunneling, now participating in the biological tunneling that keeps you alive, that powers your thoughts, that enables you to ponder your own existence. You are, quite literally, made of star stuff that has learned to think about itself. But the implications go deeper still. If consciousness plays a role in quantum mechanics, if observation somehow shapes reality at the most fundamental level, then your very act of thinking about tunneling might be participating in the cosmic dance of possibility and actuality. Each moment of awareness could be a kind of measurement, a gentle collapse of the wave function of experience into the particular now you're inhabiting. You're not just observing the universe, you're helping to create it, thought by thought, breath by breath. This leads us to perhaps the most profound question of all. If quantum tunneling allows particles to exist in multiple states simultaneously until observed, what does this mean for the nature of time and choice? Are there parallel versions of this moment, branching realities where different possibilities unfold? Are you, right now, tunneling through the barriers between potential futures, your consciousness somehow selecting which timeline to experience? The mathematics of quantum mechanics suggest that all possibilities exist in superposition until the moment of observation collapses them into a single reality. But what if consciousness itself is the mechanism by which this collapse occurs? What if your awareness is constantly tunneling through the quantum foam of possibility, choosing which version of reality to experience moment by moment? In this view, free will isn't an illusion but a fundamental feature of the universe, the means by which consciousness navigates the infinite landscape of quantum potential. This perspective transforms our understanding of choice itself. Every decision you make, every path you take, might be a kind of quantum tunneling event. Your consciousness, faced with barriers of uncertainty and possibility, somehow finds a way through to actualize one particular future from the infinite array of potential ones. The barriers between what is and what could be become permeable to the strange influence of awareness itself. And if this is true, then the very act of reading these words, of contemplating these ideas, is itself a participation in the deepest processes of the universe. Your mind tunneling through concepts and possibilities, creating meaning from the quantum foam of thought and language. Each moment of understanding, each flash of insight, a small miracle of consciousness navigating the impossible territories of knowledge and imagination. But perhaps the most remarkable aspect of this quantum view of consciousness is what it suggests about connection. If quantum entanglement links particles across vast distances, if the universe is fundamentally interconnected at the deepest level, then your consciousness might not be as isolated as it seems. The barriers between self and other, between mind and world, might be as permeable as the barriers that particles tunnel through. Your awareness, tunneling not just through possibilities, but through the apparent separations that divide one consciousness from another. This isn't mysticism, it's the logical extension of quantum mechanics into the realm of experience. If reality is fundamentally quantum, if consciousness plays a role in shaping that reality, then the boundaries we take for granted, the walls that seem to separate us from the universe and from each other, might be far more porous than we imagine. Your thoughts, your dreams, your deepest experiences might be participating in a vast cosmic conversation, a quantum dialogue between consciousness and possibility that spans the entire universe. In this view, quantum tunneling becomes more than a physical phenomenon. It becomes a metaphor for the deepest aspects of existence. The barriers between possible and actual, between self and cosmos, between one moment and the next, all become permeable to the strange influence of consciousness itself. You are not just observing the universe, you are tunneling through it, moment by moment, choice by choice, thought by thought, helping to weave the fabric of reality itself. And so we return to where we began, but with a deeper appreciation for the mystery. Particles tunnel through barriers, but perhaps consciousness tunnels through something even more profound. The barrier between potential and actual, between the many and the one, between the dreamer and the dream. In contemplating quantum tunneling, we discover that we ourselves might be the ultimate tunneling phenomenon, consciousness finding its way through the impossible territories of existence, creating meaning and reality with each passing moment of awareness. The universe, it seems, is not just stranger than we imagine, it is stranger than we can imagine. And perhaps this is the deepest mystery of all. We have journeyed through quantum equations and energy barriers, through the mathematical poetry of probability waves and the elegant dance of particles slipping through impossible walls. We have seen how quantum tunneling powers the stars, drives our technology, and enables the very chemistry of life itself. Yet here we are, conscious beings contemplating these quantum mysteries, and that contemplation itself may be the most profound quantum phenomenon of all. For consciousness, that strange flickering flame of awareness that allows you to hear these words and ponder their meaning, remains one of the greatest puzzles in science. And some researchers wonder whether consciousness itself might be intimately connected to quantum mechanics. Not in the mystical sense often portrayed in popular culture, but in ways that are both more subtle and more profound. Consider the quantum measurement problem, that curious fact that particles seem to exist in multiple states until observed. The act of measurement, of conscious observation, appears to collapse the wave function, forcing reality to choose one outcome from many possibilities. What if consciousness isn't just a passive observer of quantum tunneling, but an active participant in the quantum dance itself? Some theories suggest that consciousness might emerge from quantum processes in the brain, perhaps through quantum tunneling in neural microtubules or through quantum coherence in neural networks. The idea is controversial, and many scientists remain skeptical. But the possibility is intriguing. What if the very thoughts you're thinking right now, the awareness that allows you to contemplate these quantum mysteries, depends on particles tunneling through barriers in your neurons? If this is true, then consciousness and quantum tunneling are not separate phenomena, but two aspects of the same underlying reality. Your awareness of these words, your ability to imagine particles passing through walls, your capacity to wonder about the nature of existence itself, all might depend on the same quantum mechanical principles that allow particles to tunnel through barriers. And this brings us to a beautiful circularity. We use our consciousness to study quantum mechanics, only to discover that quantum mechanics might be the foundation of consciousness itself. The observer and the observed, the questioner and the mystery, become one continuous phenomenon. The universe isn't just something we study from the outside. We are the universe becoming aware of itself, using quantum processes to contemplate quantum processes. This perspective transforms our understanding of quantum tunneling from a mere physical curiosity into something approaching the sacred. Every time a particle tunnels through a barrier, every time a quantum wave function collapses into classical reality, the universe is making a choice, selecting one possibility from infinite potential. And perhaps, in some deep sense, consciousness is the universe's way of experiencing those choices, of feeling the weight of each quantum moment. The implications ripple outward like waves in a quantum field. If consciousness is quantum mechanical, then the boundaries between self and world, between observer and observed, become as permeable as the barriers that particles tunnel through. We are not separate from the quantum realm we study. We are expressions of it, temporary patterns in the quantum foam, brief crystallizations of awareness in an ocean of possibility. And this suggests something profound about the nature of reality itself. Perhaps the universe is not a collection of separate objects governed by mechanical laws, but a vast, interconnected web of consciousness and quantum possibility. Every particle, every wave function, every act of observation might be part of a cosmic awakening, a universal becoming aware of itself through countless perspectives and infinite quantum moments. In this view, the gentle wonder we feel when contemplating quantum tunneling isn't just an emotional response to an abstract scientific concept. It's the universe experiencing its own mystery, consciousness recognizing its quantum nature, awareness marveling at the very processes that make awareness possible. The wonder is not separate from the phenomenon it contemplates. The wonder is the phenomenon, experienced from within. And so we return to where we began, to particles that walk through walls and the quiet amazement they inspire. But now we see that the particles and the amazement might be two faces of the same quantum coin. The universe tunneling through the barriers of its own ignorance, consciousness emerging from the quantum foam like a wave that has learned to observe itself. This is the ultimate poetry of quantum mechanics, the deepest song of quantum tunneling. It's not just about particles passing through barriers. It's about the universe awakening to its own infinite possibility, one quantum moment at a time. And in that awakening, in that gentle emergence of awareness from the quantum depths, we find not just the explanation for how particles tunnel through walls, but perhaps the meaning of why there is something rather than nothing, why there is awareness rather than emptiness, why there is wonder rather than silence. The particles that walk through walls carry within them the secret of existence itself. They whisper of a reality where consciousness and cosmos dance together in eternal quantum embrace, where every act of observation is an act of creation, where every moment of awareness is a universe being born. Hello there, and welcome to a gentle journey into the quantum realm where particles dance through walls and reality bends in the most delightfully mysterious ways. Tonight's peaceful exploration is all about one of the most wondrous phenomena in physics, quantum tunneling, where the impossible becomes not just possible, but beautifully inevitable. Before we slip through the barriers of classical thinking together, I'd love to know where in the world you're watching from tonight. Are you tucked into bed with your phone glowing softly in the darkness? Perhaps you're in a cozy chair with a warm cup of tea, watching the world settle into evening. There's something rather fitting about discussing particles that slip through walls, while we ourselves are safely contained within our own comfortable walls. If you find this voyage through quantum mysteries soothing, intriguing, or simply a lovely way to let your mind wander into the strange and beautiful corners of the universe, I'd be ever so grateful if you gave this video a like. It helps this little corner of scientific wonder reach others who might need a peaceful pause filled with cosmic curiosities. Now, I do hope this isn't so fascinating that it keeps you awake, but if it does, well, at least you'll drift off knowing something extraordinary about the hidden nature of reality itself. So settle in, let your thoughts slow like autumn leaves finding their way to Earth, and let's begin this gentle descent into the quantum world. Imagine, if you will, that you're walking toward a brick wall. In our everyday world, you'd stop when you reached it, perhaps place your hand against its solid surface, feel its rough texture and unyielding strength. The wall is there, you are here, and that's simply how things are. But in the quantum realm, in that strange and wonderful world that exists beneath the surface of everything we see and touch, something rather extraordinary happens. A particle approaching that same wall doesn't always stop. Sometimes, in defiance of everything our daily experience tells us should happen, it simply appears on the other side. Not over the wall, not around it, not through some convenient hole, but through the wall itself, as if the barrier were nothing more than morning mist. This is quantum tunneling, and it's one of the most beautifully counterintuitive phenomena in all of physics. The very name conjures images of particles digging tiny tunnels through matter, like microscopic miners with impossibly small pickaxes. But the reality is far more elegant and mysterious than that. There are no tunnels, no drilling, no conventional passage through space. Instead, there's something far more profound happening, something that touches the very heart of what it means to exist in this quantum universe. To understand this gentle magic, we must first embrace a rather curious fact about the quantum world. Down at the scale of atoms and subatomic particles, the familiar rules of location and movement begin to blur like watercolours in the rain. A particle doesn't have a precise location in the way a chair has a location in your room. Instead, it exists as what physicists call a wave function, a mathematical description of probability that spreads out through space like ripples on a pond. This wave function tells us not where the particle is, but where it might be found if we were to look for it. It's rather like having a friend who's always moving about town, and instead of knowing exactly where they are at any given moment, you have a map showing the likelihood of finding them in various places. The coffee shop might have a high probability, the library somewhat less, and the top of the local cathedral tower virtually none at all. But here's where things become truly wonderful. When this probability wave encounters a barrier, something remarkable happens. In our everyday world, waves can do something rather clever when they meet obstacles. Ocean waves can wrap around the pillars of a pier. Sound waves can bend around corners, allowing you to hear someone calling from another room. This is called wave diffraction, and it's a perfectly normal, though often unnoticed, part of our world. The quantum wave function behaves similarly, but with consequences that stretch far beyond the merely physical. When a particle's probability wave encounters a barrier, it doesn't simply stop at the wall like a ball bouncing off a surface. Instead, part of the wave continues on the other side, though usually much diminished, like an echo of its former self. This means that there's always some probability, however small, that the particle will be found on the far side of the barrier. And here's the truly magical part. In the quantum world, probability isn't just a mathematical abstraction, it's the very fabric of reality itself. If there's a probability of finding the particle beyond the wall, then sometimes, wonderfully and mysteriously, that's exactly where it will be. The mathematics of this phenomenon are surprisingly elegant. The probability of tunneling depends on several factors: the width of the barrier, its height in terms of energy, and the energy of the particle itself. A thin barrier is more easily tunneled through than a thick one, rather like how it's easier to whisper through a thin wall than a thick one. A particle with more energy has a better chance of tunneling, though even very low energy particles can sometimes manage the feat. But perhaps the most beautiful aspect of quantum tunneling is its universality. This isn't some exotic phenomenon that only occurs in the most extreme conditions or the most carefully controlled laboratory experiments. It's happening all around us all the time, in ways both subtle and profound. The sun itself owes its existence to quantum tunneling. In the core of our star, hydrogen nuclei are trying to fuse together to form helium, releasing the energy that eventually becomes the sunlight streaming through your window. But there's a problem. These hydrogen nuclei are positively charged, and positive charges repel each other with tremendous force. The nuclei don't have enough energy to overcome this electrical barrier through classical means. Yet fusion happens anyway, billions of times per second, because the nuclei can tunnel through the electrical barrier that should keep them apart. Without quantum tunneling, the sun would be a cold, dark ball of hydrogen, and none of us would be here to wonder about the mysteries of the quantum world. Every ray of sunlight, every warm day, every flower that blooms in spring exists because particles can walk through walls. The phenomenon extends far beyond stellar fusion. In the electronic devices that surround us, quantum tunneling plays a crucial role. The flash memory in your phone, the hard drive in your computer, even the simple act of plugging in a device and having electricity flow through the connection all depend on the quantum mechanical ability of electrons to tunnel through barriers that should, by all classical reasoning, be impenetrable. There's something deeply poetic about this. The very words you're reading now, displayed on a screen that relies on quantum tunneling, are reaching your eyes thanks to the same phenomenon that powers the sun. The universe has woven this quantum thread through the fabric of reality at every scale, from the cosmic to the microscopic, from the profound to the everyday. But quantum tunneling also reveals something beautiful about the nature of possibility itself. In our daily lives, we often think of barriers as absolute. A wall stops us, a locked door keeps us out, a mountain blocks our path. We learn to work around these obstacles, to find alternative routes, to accept the limitations they impose. The quantum world whispers a different story. It suggests that barriers, no matter how formidable they appear, are never absolute. There's always some probability, some chance, some whisper of possibility that the impossible might occur. The probability might be vanishingly small, so tiny that we'd have to wait longer than the age of the universe to see it happen. But it's never quite zero. This isn't to say that we should expect to walk through walls ourselves. The quantum effects that allow particles to tunnel become negligibly small for objects much larger than atoms. The probability of a person tunneling through a wall is so incredibly tiny that it's essentially zero for all practical purposes. But there's something comforting about knowing that the universe, at its deepest level, is a place where absolute barriers don't exist. As we drift deeper into this quantum landscape, we begin to see that tunneling is just one expression of a more fundamental truth about reality. The quantum world is not a world of definite positions and predetermined paths. It's a world of probabilities and possibilities, of gentle uncertainties and beautiful ambiguities. In this realm, a particle doesn't travel from point A to point B along a single, well-defined trajectory. Instead, it explores all possible paths simultaneously, including paths that take it through barriers, around obstacles, and even backward through time. The path we observe, the one that appears in our measurements and experiments, is just one thread in a vast tapestry of quantum possibilities. This multiplicity of paths is captured in something called the path integral formulation of quantum mechanics, developed by the brilliant physicist Richard Feynman. In this picture, a particle travelling from one point to another simultaneously takes every conceivable path between those points. Most of these paths cancel each other out through quantum interference, leaving only the most probable path visible in our everyday experience. But some paths, including those that tunnel through barriers, contribute to the final probability in ways that can be measured and observed. And the universe responds by allowing all possibilities to coexist until the moment of observation collapses them into a single, definite outcome. This quantum superposition of possibilities extends to the act of tunneling itself. Before we measure where the particle is, it exists in a superposition of being on both sides of the barrier simultaneously. The act of measurement doesn't reveal where the particle was. It determines where the particle is, collapsing the wave function into a definite state. There's something almost meditative about this picture of reality. In our hurried, goal-oriented world, we often focus intensely on destinations and outcomes. But the quantum world suggests that the journey itself, with all its myriad possibilities and potential paths, is where the real richness lies. The particle doesn't struggle against the barrier or search frantically for a way around it. It simply explores all possibilities with equal quantum equanimity. This exploration of possibilities happens on timescales that are almost incomprehensibly brief. The act of tunneling typically occurs in femtoseconds or attoseconds, timeframes so short that light itself can barely travel the width of an atom. Yet, in these infinitesimal moments, the fundamental nature of reality reveals itself in all its quantum glory. The speed of tunneling has puzzled physicists for decades. When a particle tunnels through a barrier, how long does it spend inside the barrier? This question, known as the tunneling time problem, touches on deep issues about the nature of time itself in quantum mechanics. Some experiments suggest that particles can tunnel through barriers instantaneously or even appear to exit the barrier before they enter it, leading to apparent faster-than-light travel. These results don't violate Einstein's relativity, because no information or energy is transmitted faster than light. Instead, they reveal the subtle and counterintuitive nature of quantum time. The particle doesn't travel through the barrier in the conventional sense. It simply transitions from one probability state to another, and our classical notions of travel time become meaningless. This timeless quality of quantum tunneling adds another layer to its mystery and beauty. In a world where we're constantly aware of time passing, where every moment is measured and scheduled, there's something liberating about a phenomenon that occurs outside the normal flow of time. The particle doesn't wait, doesn't hesitate, doesn't spend time overcoming the barrier. It simply is on one side, and then it is on the other, with the transition itself existing in a quantum realm beyond our everyday experience of duration. As we continue our gentle journey through the quantum landscape, we begin to see that tunneling is not just a curious physical phenomenon, but a window into the deepest mysteries of existence itself. It challenges our assumptions about the nature of reality, the meaning of possibility, and the relationship between the observed and the observer. In the quantum world, the very act of observation changes what we observe. The particle's wave function, spread out in probability across space, collapses into a definite position when we measure it. This means that the reality we observe is not independent of our observation. It's created, in part, by the act of looking. This observer effect adds a deeply personal dimension to quantum tunneling. Every time we detect a particle that has tunneled through a barrier, we're not just observing a physical event, we're participating in the creation of reality itself. The universe is not a collection of objects moving through space according to predetermined laws. It's a dynamic, interactive system where consciousness and cosmos dance together in an eternal quantum waltz. The implications of this dance extend far beyond the realm of physics. If reality is fundamentally probabilistic, if barriers are never absolute, if observation creates as much as it discovers, then perhaps our own lives are more malleable, more open to possibility than we might have imagined. The quantum world doesn't tell us how to live, but it whispers gently that the universe is far stranger, far more wonderful, and far more full of potential than our everyday experience suggests. As we near the end of our first gentle exploration into the realm of quantum tunneling, we find ourselves in a place both familiar and utterly transformed. The world around us looks the same, but we now know that beneath its solid, predictable surface lies a realm of infinite possibility, where particles dance through walls as easily as light streams through windows. This knowledge doesn't change the practical reality of our daily lives. Walls still stop us, Doors still need to be opened, mountains still present challenges to be overcome. But it does suggest that the universe is far more generous with possibility than we might have thought. In the quantum realm, every barrier is permeable, every obstacle is surmountable, every impossibility carries within it the seed of its own transcendence. The mathematics may be complex, the experiments may require sophisticated equipment, but the heart of quantum tunneling is beautifully simple. Particles can go where classical physics says they cannot go. They do this not through force or cleverness, but through the simple, elegant fact that in the quantum world, probability is reality, and reality always leaves room for the impossible. As you settle into sleep tonight, carried along by the gentle current of quantum possibilities, remember that you exist in a universe where particles walk through walls as naturally as fish swim through water. The same quantum fields that allow for tunneling flow through every atom in your body, connecting you to the stars, to the Earth, to the vast network of possibility that underlies all existence. Tomorrow, when you wake and go about your day, the quantum world will continue its silent, invisible work all around you. Electrons will tunnel through barriers in your devices, allowing you to connect with others across vast distances. The sun will continue its fusion dance powered by particles that refuse to be stopped by electrical barriers. And somewhere in the quantum foam that underlies all reality, possibilities will continue to unfold. Barriers will continue to be permeable, and the impossible will continue to whisper its quiet invitation to wonder. In this first part of our journey, we've glimpsed the gentle magic of quantum tunneling, seen how particles can slip through barriers that should stop them, and touched on the profound implications this has for our understanding of reality itself. We've discovered that the universe is not a collection of solid, impenetrable objects, but a flowing tapestry of probabilities and possibilities, where every barrier is an invitation to transcendence. The quantum world is calling, with its promise of deeper mysteries and more profound wonders. Welcome back to this exploration of the quantum realm where the impossible becomes everyday reality, and the very foundations of what we consider solid begin to shimmer like heat waves on a summer's day. We've established that particles can indeed walk through walls, that the universe operates on principles of probability rather than certainty, and that barriers exist more as suggestions than absolute blockades. But now we must venture deeper into this strange landscape, because quantum tunneling is just the beginning of a story that reshapes everything we thought we knew about the nature of reality itself. Picture, if you will, a universe where nothing is quite what it seems, where the act of looking changes what you're looking at, where particles exist in multiple states simultaneously until the moment of observation collapses them into a single reality, and where the very concept of a definite position or momentum becomes as elusive as trying to hold water in your hands. This is the world that quantum tunneling emerges from, a world governed by the Schrödinger equation, that elegant mathematical poem that describes how quantum systems evolve over time. The equation itself is deceptively simple in its written form, yet it contains within it the seeds of profound mystery. It tells us that every particle, every quantum system, exists not as a definite thing in a definite place, but as a wave function, a mathematical description of all possible states that system could be in. Think of it as nature's way of keeping its options open, of refusing to commit to any single outcome until absolutely forced to do so. But here's where the story becomes truly fascinating. The wave function doesn't just describe where a particle might be found, it describes the probability of finding it in any given location. And these probabilities, these ghostly mathematical entities, follow rules that seem to mock our everyday experience. They can interfere with each other, creating patterns of enhancement and cancellation that determine where a particle is likely to appear and where it definitely won't. It's as if reality itself is playing a cosmic game of hide and seek, using the rules of wave interference to determine the outcome. When we apply this quantum mechanical picture to the phenomenon of tunneling, something remarkable emerges. The particle approaching a barrier doesn't simply bounce off like a tennis ball hitting a wall. Instead, its wave function, that mathematical description of all its possible states, extends beyond the barrier. Even though classical physics would say the particle lacks the energy to surmount the obstacle, quantum mechanics whispers a different story. The wave function seeps through the barrier like water through a sieve, carrying with it the probability that the particle might be found on the other side. This is where the uncertainty principle, that cornerstone of quantum mechanics, makes its presence felt. Formulated by Werner Heisenberg, this principle tells us that there are fundamental limits to how precisely we can know certain pairs of properties simultaneously. The more precisely we try to measure a particle's position, the less precisely we can know its momentum, and vice versa. It's not a limitation of our measuring instruments, but a fundamental feature of reality itself. In the context of tunneling, this uncertainty becomes a doorway to the impossible. The barrier represents a region where classically the particle should never be found. But quantum mechanics allows for fluctuations, brief moments where the particle can borrow energy from the vacuum itself, energy that must be paid back so quickly that the universe's accounting system doesn't have time to notice. During these fleeting instants, the particle can exist in the classically forbidden region, and if the barrier is thin enough, it can emerge on the other side before the cosmic debt collector comes calling. The mathematics of this process is both beautiful and bewildering. The wave function that describes the tunneling particle takes on an exponential form within the barrier, decaying rapidly as it penetrates deeper into the forbidden region. The probability of tunneling depends critically on the width and height of the barrier, decreasing exponentially with both. This is why tunneling is more pronounced for lighter particles like electrons, and why it becomes vanishingly unlikely for objects of everyday size. The universe, it seems, reserves its most magical tricks for the smallest scales. But quantum tunneling is more than just a mathematical curiosity. It's a window into the deeper workings of the quantum world, where the classical concepts of definite position and momentum give way to a more fluid, probabilistic reality. In this realm, particles don't follow predetermined paths, but instead explore all possible routes simultaneously, only settling on a specific trajectory when forced to do so by measurement or interaction. This multiplicity of paths is captured beautifully in the path integral formulation of quantum mechanics, developed by Richard Feynman. In this picture, a particle travelling from point A to point B doesn't take a single path, but instead takes every possible path simultaneously. Each path contributes to the overall probability amplitude, and the particle's actual behaviour emerges from the interference between all these ghostly trajectories. For tunneling, this means that the particle doesn't simply punch through the barrier in a straight line. Instead, it explores every conceivable route around, over, and through the obstacle. Most of these paths cancel each other out through interference, but some survive and contribute to the tunneling probability. The particle, in a sense, finds its way through the barrier by trying every possible approach at once. This quantum superposition of paths leads to phenomena that would be impossible in a classical world. A particle can tunnel through a barrier faster than light would travel the same distance in free space, not because it's moving faster than light, but because its wave function explores shortcuts through the quantum landscape that classical physics cannot access. Time itself becomes negotiable in the quantum realm, with particles arriving at their destinations before they've had time to properly traverse the intervening space. The implications of this quantum behaviour extend far beyond the realm of physics textbooks. In the quantum world, the very act of observation plays a crucial role in determining reality. Before measurement, the particle exists in a superposition of all possible states, simultaneously inside and outside the barrier, transmitted and reflected. Only when we attempt to detect it does the wave function collapse, forcing the particle to choose a definite outcome. This observer effect isn't just a quirk of quantum mechanics, it's a fundamental feature of how information flows in the universe. The quantum system and the measuring apparatus become entangled, their fates intertwined in a way that defies classical understanding. The barrier itself becomes part of this quantum dance, its properties influencing not just whether tunneling occurs, but how the very process of measurement unfolds. As we delve deeper into the quantum realm, we discover that tunneling is just one manifestation of a more general principle. The universe is fundamentally probabilistic, not deterministic. What we perceive as solid, impenetrable barriers are actually regions of reduced probability, speed bumps in the quantum landscape, rather than absolute walls. The particle wave function, that mathematical ghost that haunts quantum mechanics, carries within it the seeds of all possible futures, all potential outcomes waiting to be realized. This probabilistic nature of reality has profound consequences for our understanding of causality and time. In the quantum world, effects can precede causes. Particles can influence each other instantaneously across vast distances, and the future can reach back to influence the past. The tunneling particle doesn't just cross the barrier, it exists in a state of quantum superposition that encompasses all possible histories and futures until the moment of measurement collapses this multiplicity into a single, definite outcome. The beauty of quantum tunneling lies not just in its practical applications or its violation of classical intuition, but in what it reveals about the nature of reality itself. We live in a universe where the impossible is merely improbable, where barriers are invitations rather than prohibitions, and where the very act of observation participates in the creation of reality. Every quantum tunneling event is a small miracle, a reminder that the universe is far stranger and more wonderful than our classical minds can fully grasp. In this quantum landscape, the particle approaching the barrier carries with it the entire history of the universe encoded in its wave function. Every interaction it has ever had, every force that has ever acted upon it, contributes to the complex probability amplitude that determines its fate. The barrier itself is not just a static obstacle, but a dynamic participant in the quantum drama, its properties shaped by the same probabilistic laws that govern the particle's behavior. As we continue to explore this quantum wonderland, we begin to see that tunneling is not just a phenomenon, but a principle, a fundamental way in which the universe operates. It's a reminder that reality is far more flexible, far more creative than we ever imagined. The walls that seem so solid in our everyday experience are revealed to be mere suggestions, gentle guidelines that the universe follows most of the time, but is perfectly willing to ignore when the quantum mood strikes. This flexibility, this fundamental permeability of reality, suggests that we live in a universe of infinite possibility, where the impossible is always just one quantum fluctuation away. The particle doesn't overcome the barrier through brute force, but through the elegant application of quantum probability, finding pathways through the mathematical landscape that classical physics cannot even imagine. Now, let's turn our attention to something truly remarkable about quantum tunneling that touches the very core of what makes us human. Because here's the thing about this strange quantum phenomenon. It's not just happening in distant stars or laboratory experiments tucked away in university basements. It's happening right now, in the cells of your body, in the technology that surrounds you, and in ways that quite literally keep you alive. Consider for a moment the gentle warmth you feel from sunlight streaming through a window. That warmth, that life-giving energy, exists because of quantum tunneling happening millions of miles away in the heart of our sun. Deep within the solar core, hydrogen nuclei are trying to fuse together to create helium, but they face an enormous barrier. These positively charged particles repel each other with tremendous force, like trying to push two powerful magnets together with their matching poles facing. Classical physics would say this fusion is impossible at the temperatures and pressures found in the sun's core. The barrier is simply too high, too strong, too impenetrable. But quantum tunneling whispers a different story. Those hydrogen nuclei, existing as probability waves rather than solid little balls, can tunnel through the electromagnetic barrier that should keep them apart. It's not that they climb over the barrier or break it down, they simply appear on the other side, fuse together, releasing the energy that eventually becomes the sunlight warming your face. Without quantum tunneling, the sun would be a cold, dark sphere of hydrogen, and we wouldn't be here to wonder about any of this. The beautiful irony is that nuclear fusion in stars was one of the great puzzles of early 20th century physics. Scientists knew the sun was burning far too brightly for far too long, given the temperatures they calculated at its core. The classical physics of the time suggested our sun should have burned out long ago. It wasn't until quantum mechanics revealed the reality of tunneling that we understood how stars actually work. The universe had been keeping its secret all along, hidden in the probabilistic dance of quantum particles. This same process powers every star you see twinkling in the night sky. Each point of light represents a massive nuclear furnace, where quantum tunneling transforms simple hydrogen into heavier elements, releasing the energy that travels across vast distances to reach your eyes. The carbon in your body, the oxygen you breathe, the calcium in your bones, all of these elements were forged in the hearts of ancient stars through quantum tunneling events, scattered into space when those stars died, and eventually incorporated into the planet where you now sit, contemplating their journey. But quantum tunneling isn't just a cosmic phenomenon. It's woven into the fabric of modern technology in ways that would seem almost magical to previous generations. The device you're using to listen to these words, whether it's a smartphone, tablet, or computer, relies on quantum tunneling to function. Inside the microprocessors that power these devices are billions of tiny transistors, each one a quantum switch that controls the flow of electrical current. These transistors work by creating barriers that electrons can tunnel through or be blocked by, depending on the voltage applied. When you tap a screen, type a message, or stream a video, you're orchestrating trillions of quantum tunneling events per second. The smooth operation of your digital world depends on our ability to harness and control this quantum phenomenon with extraordinary precision. The scanning tunneling microscope, one of the most powerful tools in modern science, takes this principle even further. It uses quantum tunneling to create images of individual atoms. A tiny needle is brought incredibly close to a surface, close enough that electrons can tunnel between the needle and the atoms below. By measuring these tunneling currents as the needle moves across the surface, scientists can map the positions of individual atoms with breathtaking precision. It's like using quantum mechanics as a flashlight to illuminate the fundamental building blocks of matter. Flash memory, the technology that stores your photos, music, and documents, also depends on quantum tunneling. Information is stored by trapping electrons in tiny quantum wells, and these electrons can only escape by tunneling through barriers. When you save a file or take a picture, you're creating patterns of trapped electrons that will remain stable for years, held in place by the same quantum barriers that occasionally let particles slip through. Even more remarkably, quantum tunneling plays a crucial role in the chemistry of life itself. Many biological processes involve electrons tunneling between molecules, enabling reactions that would be impossible under classical physics. The process of photosynthesis, which converts sunlight into chemical energy in plants, involves quantum tunneling events that help transfer energy with remarkable efficiency. The very fact that plants can capture and convert solar energy so effectively may depend on their ability to exploit quantum mechanical effects. Enzymes, the molecular machines that catalyze chemical reactions in living organisms, often work by lowering energy barriers just enough to allow quantum tunneling to occur. These protein structures have evolved over billions of years to create the perfect conditions for specific tunneling events, enabling the complex chemistry of life to unfold at the temperatures and pressures found in biological systems. There's even evidence that quantum tunneling might play a role in how we experience smell. Some scientists propose that our olfactory system doesn't just recognize the shape of odor molecules, but also detects their vibrational frequencies through quantum tunneling effects. When molecules bind to receptors in your nose, electrons might tunnel across the molecular gap, creating unique electrical signatures that your brain interprets as different scents. It's a theory that's still being investigated, but it suggests that even our sensory experiences might be fundamentally quantum mechanical. The implications go deeper still. DNA, the molecule that carries genetic information, occasionally undergoes mutations due to quantum tunneling. Hydrogen atoms in the base pairs that make up the genetic code can tunnel to different positions, temporarily changing the shape of the DNA and potentially causing errors when the molecule is copied. While this might sound alarming, it's actually one of the driving forces of evolution. These quantum-induced mutations provide the genetic variation that allows species to adapt and evolve over time. In the world of renewable energy, quantum tunneling is opening new possibilities. Solar cells are being designed to exploit tunneling effects to improve their efficiency. Quantum dots, tiny semiconductor particles, can be engineered to create tunneling pathways that allow electrons to move more freely, potentially leading to solar panels that capture more of the sun's energy and convert it into electricity. Researchers are also exploring how quantum tunneling might be used in quantum computing, where information is processed using quantum bits or qubits that can exist in multiple states simultaneously. Quantum tunneling could provide a way to control and manipulate these qubits, potentially leading to computers that can solve certain problems exponentially faster than classical machines. But perhaps the most profound realization is that quantum tunneling reveals something fundamental about the nature of reality itself. The fact that particles can pass through barriers that should be impenetrable suggests that the universe operates according to principles that are far more subtle and interconnected than our everyday experience suggests. The boundaries that seem so solid and definite in our macroscopic world are, at the quantum level, more like gentle suggestions than absolute rules. This has philosophical implications that extend far beyond physics. If the fundamental particles that make up everything we see and touch can transcend apparent limitations, what does this say about the nature of possibility itself? Quantum tunneling reminds us that the universe is far stranger and more wonderful than it appears on the surface, full of hidden pathways and unexpected connections. As you sit here listening to these words, quantum tunneling events are occurring throughout your body, in the technology around you, and in the stars overhead. You are part of a vast quantum symphony, where particles dance through barriers and possibilities unfold in ways that defy classical intuition. The solid world you perceive is, at its deepest level, a shimmering tapestry of probabilities and tunneling events. So the next time you feel the warmth of sunlight, use your smartphone, or simply breathe the air around you, remember that you're experiencing the practical consequences of one of the most mysterious and beautiful phenomena in the universe. Welcome back to this gentle exploration of the quantum realm, where we continue our journey through the looking glass of reality itself. We've seen how particles dance between possibilities, how waves of probability ripple through barriers, and how the very act of observation shapes the universe around us. Now, as we settle deeper into this quantum wonderland, we encounter perhaps the most beautiful paradox of all, how quantum tunneling reveals that the universe operates not on certainty, but on an endless symphony of maybes. Picture, if you will, a cosmic game of chance where the house always wins, yet somehow, impossibly, the players keep finding secret passages through the walls. This is the deeper truth of quantum tunneling, a phenomenon that whispers to us about the fundamental nature of reality itself. It's not merely that particles can slip through barriers, it's that the entire fabric of existence is woven from threads of probability, each strand vibrating with infinite potential. Consider the electron in your smartphone's processor, making its quantum leap through silicon barriers thousands of times per second. Each tunneling event is a small miracle, a moment where the particle exists in a state of pure possibility before choosing its path. Yet this choosing isn't conscious, isn't deliberate. It's something far more mysterious, the universe expressing its deepest preferences through the language of mathematics and chance. The wave function that describes this electron doesn't simply calculate where it might be. It embodies every possible story the particle could tell. Before measurement, before interaction, the electron exists as a ghost of all its potential selves, each version equally real in the quantum sense. When tunneling occurs, we witness the collapse of infinite possibilities into a single actuality, like watching a symphony of potential resolve into one perfect note. This brings us to one of the most profound implications of quantum tunneling, the role of information in shaping reality. When a particle tunnels through a barrier, it carries with it a kind of quantum signature, a fingerprint of its journey through the impossible. This information doesn't disappear, it becomes entangled with the environment, creating what physicists call decoherence. The pristine quantum state dissolves into the messy, classical world we inhabit, yet traces of its quantum nature linger like morning mist. The beauty of this process lies in its delicate balance. Too much interaction with the environment, and the quantum behavior vanishes entirely. Too little, and the particle remains trapped in its probabilistic limbo, unable to tunnel at all. There's a sweet spot, a Goldilocks zone of quantum mechanics where tunneling flourishes. It's here that we find the universe at its most creative, neither fully determined nor completely random, but something exquisitely in between. This quantum creativity extends far beyond individual particles. In the depths of space, quantum tunneling plays out on scales both vast and minute. In the heart of neutron stars, where matter is compressed to unimaginable densities, quantum effects create structures that classical physics cannot explain. Particles tunnel through barriers of pure energy, creating pathways for matter to exist in states that should be impossible. These stellar laboratories reveal quantum mechanics operating at the very limits of physical law. Back on Earth, life itself has learned to harness this quantum creativity. The process of photosynthesis, by which plants convert sunlight into chemical energy, relies on quantum tunneling in ways that continue to astound scientists. Electrons tunnel through protein barriers with an efficiency that seems almost supernatural, guided by quantum coherence that persists even in the warm, wet environment of living cells. It's as if evolution has discovered how to choreograph quantum dances, teaching molecules to waltz through barriers that should stop them cold. The quantum tunneling in biological systems reveals something profound about the relationship between order and chaos. Living organisms exist at the edge of thermodynamic equilibrium, neither fully stable nor completely random. In this liminal space, quantum effects can persist long enough to influence biological processes. The boundary between the quantum and classical worlds becomes blurred, creating opportunities for life to exploit quantum advantages while maintaining classical reliability. This intersection of quantum mechanics and biology has given birth to an entirely new field, quantum biology. Scientists now understand that quantum tunneling plays a role in enzyme catalysis, the process by which biological molecules accelerate chemical reactions. The enzyme creates a quantum environment where reactants can tunnel through energy barriers, dramatically increasing reaction rates. It's a molecular magic trick that has been performed billions of times per second in every living cell for billions of years. Perhaps most remarkably, quantum tunneling may play a role in consciousness itself. Some researchers propose that quantum effects in the brain's microtubules, the scaffolding structures within neurons, could give rise to conscious experience. While this remains highly speculative, the idea that our thoughts might emerge from quantum processes is deeply poetic. If true, it would mean that consciousness itself is a form of quantum tunneling, a leap across the barrier between matter and mind. The philosophical implications of quantum tunneling extend even further. If particles can tunnel through barriers, what does this say about the nature of boundaries themselves? In the quantum world, walls are not absolute barriers but probability landscapes. The stronger the wall, the less likely tunneling becomes, but the possibility never quite reaches zero. This suggests that, in the deepest sense, nothing is truly impossible, only more or less probable. This quantum perspective on possibility has profound implications for how we understand causality. In classical physics, causes precede effects in a neat, linear chain, but quantum tunneling introduces a kind of temporal fuzziness. The tunneling event itself exists in a superposition of having happened and not having happened until the system is observed. This creates what physicists call quantum causality, where the relationship between cause and effect becomes probabilistic rather than deterministic. The technology emerging from our understanding of quantum tunneling continues to push the boundaries of what's possible. Quantum computers rely on tunneling effects to perform calculations that would take classical computers longer than the age of the universe. These machines don't just process information, they explore multiple computational paths simultaneously, tunneling through the space of possible solutions to find answers with unprecedented speed. In the field of quantum sensing, tunneling effects are being used to create instruments of extraordinary precision. Quantum magnetometers can detect magnetic fields so weak they would be lost in the noise of classical sensors. These devices work by allowing quantum states to tunnel between different energy levels, creating interference patterns that reveal the presence of incredibly subtle environmental changes. It's as if we've learned to read the universe's whispers. The future promises even more remarkable applications. Quantum tunneling might enable new forms of energy storage, where electrons tunnel through carefully engineered barriers to create batteries that charge in seconds and last for decades. Solar cells based on quantum tunneling could harvest energy from parts of the electromagnetic spectrum that current technology ignores, dramatically increasing the efficiency of renewable energy systems. Perhaps most intriguingly, quantum tunneling might offer insights into the nature of time itself. Some theories suggest that time's arrow, the direction from past to future, emerges from quantum processes. If particles can tunnel through barriers in space, might they also tunnel through barriers in time? This remains purely speculative, but it hints at deeper connections between quantum mechanics and the fundamental structure of reality. As we contemplate these possibilities, we're reminded that quantum tunneling is more than just a curious phenomenon. It's a window into the deepest mysteries of existence. It reveals a universe where the impossible is merely improbable, where barriers are invitations rather than prohibitions, and where the very act of observation participates in the creation of reality. In this quantum universe, we find ourselves not as passive observers, but as active participants in an ongoing cosmic conversation. Every measurement we make, every quantum system we observe, adds to the grand dialogue between possibility and actuality. We are, in a very real sense, co-creators of the reality we inhabit, our consciousness intertwined with the quantum processes that govern the behavior of matter and energy. The story of quantum tunneling is ultimately a story about the nature of existence itself. It tells us that reality is not a fixed stage on which events play out, but a dynamic, ever-changing landscape of possibilities. In this landscape, particles tunnel through barriers, waves interfere with themselves, and the very act of observation shapes what we observe. It's a universe of infinite creativity, where the impossible becomes inevitable given enough time and space. As we drift toward the conclusion of our quantum journey, we carry with us the profound realization that we live in a universe where magic is not supernatural, but natural, where the impossible is not forbidden, but merely improbable, and where the deepest truths about reality can only be glimpsed through the gentle, persistent act of scientific curiosity. In the quantum realm, wonder is not just an emotion, it's a fundamental feature of existence itself.